Welcome, everyone. My name is Joel Sprague, and I am the session chair of this session. The session is titled Advancements in Sediment Control. A couple of things to note before we start the presentations. You will have the opportunity to ask questions during this on-demand session by clicking the Questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PBH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you need to include the verification code shown in this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations.
Hello, everyone. Welcome to the Virtual Geosynthetics Conference. My name is Blake Whitman. I'm an assistant professor at Middle Tennessee State University, and I'm going to be presenting technologies used for sediment control. How are they tested, and how do they perform? So, first of all, how are geotextiles used in sediment control? So, these are typically implemented in silt fence installations. This can be done many different ways, but the overall intent is for the geotextile fabric to be installed vertically, and eventually we want it to contain sediment and release stormwater. So it'll impound sediment-laden flows, allow soil particles to fall out of suspension, and then slowly release water over time. This is what we intended to do. However, this is not always what happens. So there are some current ASTM standards that are out there that we can use to test different types of erosion and sediment control practices. We essentially have a small scale and a large scale. So ASTM D5141, this is the standard test method for determining filtering efficiency, flow rate, and the filtration component of a sediment retention device is what I consider a small scale test. We also have ASTM D7351, which is the standard test method for determination of sediment retention devices' effectiveness in sheet flow applications. So, what we've noticed with these two ASTM tests is that they introduce limited flow in sediment when you actually run the test. So it's not necessarily representative for all areas of the nation or the world. And it doesn't mimic realistic runoff conditions. So therefore, there is a need to identify accurate sediment retention capabilities and flow rates, as well as water quality impacts. So we set out to develop two new test standards, essentially a small scale and a large scale test standard that can provide us more realistic results depending on where the sediment control device is going to be installed. So we'll start with the small scale testing. So what I'm showing here is the actual ASTM D5141 design specs that is provided, as well as an image that has been constructed. So essentially, a 20-gallon container will be filled with water and sediment based off the specifications. It'll be mixed up, and then that is introduced into roughly a 4-foot long by 3-foot wide box where at the end of it a geotextile is attached. And this is the current standard for testing geotextiles. What we set out to do is to develop a more in-depth testing process where we can actually have full-scale geotextile installations, but do it on a small width component, essentially. So what we developed was this testing box, essentially, where I introduce water and sediment. It comes down a 3-to-1 horizontal slope, which we designed based off cut and fill operations, typically on roadside construction projects. Then it enters the bottom portion of the box, which is on a 1% slope, and we install a geotextile that is actually 3 feet in height. And what's completely different about this particular testing process compared to the ASTM is that we actually introduce flow and sediment over a 30-minute duration, instead of just filling up a 20-gallon container, mixing it, and then releasing it to the geotextile. And we can adjust the flow that's being introduced as well as the amount of sediment based off calculations for geographical locations. When we install the geotextile, we line the wooden box with a polypropylene liner. That way flow cannot escape through the cracks. And we also caulk the geotextile to the polypropylene liner. That way we ensure that all flow actually passes through the geotextile and that there's no flow bypass. We introduce flow using a water tank. So we have a submersible pump that pumps into the tank, and on the opposite side of the tank that is not shown, we actually have a discharge weir. And based off the water height flowing across the discharge weir, we can actually adjust the flow rate just using the outflow valves. So this is what the front of that discharge weir actually looks like. And the flow will actually exit the weir and enter this little mixing trough that we have constructed. And this is where our sediment will be introduced over the duration of the test. So when we built this, we have initially did 5 geotextile fabric evaluations. We did a non-woven needle punched, we did a non-woven spun bound, and then we did 3 monofilament geotextiles. And we just refer to them as blue stripe, red stripe, and green stripe because this is how they're actually constructed. So you can actually tell the difference just by looking at the geotextile. Each one of them is a little bit different, but we don't have time to go into those specifications. When we ran these small scale tests on these different sediment control geotextiles, we found that the needle punch and the spun bound gave us a 97 and 98% sediment retention based off dry weights of sediment retained upstream. So we knew the weight of dry soil going in. We collected the soil when the testing was done. We dried it in ovens. So we had a mass balance sediment retention. We also did this with the monofilament geotextiles. We found that blue stripe gave us an average of 87%, red stripe 94%, and green stripe 93%. So one thing to mention about the small scale testing is it is a very good test if you're just wanting to identify the performance of a specific geotextile, not necessarily the installation of the silt fence. So if you just want to test the geotextile itself, this is an ideal test to use. And there's more about this online in publications that we've done. Now switching over to large scale testing. So ASTM D7351 outlines using a larger mixing tank and actually allowing that flow to actually discharge onto a ramp where you actually have some type of sediment barrier practice installed. This can be hay bales, it can be silt fence, it can be any type of practice that's out there available. And then you collect water samples and data and sediment retention analysis and all that based off the ASTM standard. So what we set out to do is create a larger sediment barrier test apparatus that uses that same methodology where we can control sediment over a 30-minute test duration as well as water. So we constructed a 20-foot ride sediment barrier testing apparatus that has an equilibrium tank to introduce water. It has a sediment hopper to introduce soil. That flow is in discharge onto an impervious weir, and then it hits diversion veins and turns into sheet flow. And then down in the earthen test area, we can install a full-length, full-scale sediment barrier so we can actually evaluate not only the material, but the way it is actually installed as well. And then we have a collection tank downstream where we can collect flow and actually monitor flow rates through this particular setup. And then most recently, we installed pole barns over the entire testing apparatus so that when we're doing these full-scale testing, and a natural rain event occurs, it doesn't mess up our test data. So just to give you an idea of what a standard silt fence performs, so this is how AlDOT used to have their standard silt fence installations designed. So it was a geotextile installed with 0.95 pound per foot T-post spaced 10 feet. And after 3 simulated storm events, we realized that the geotextile fence actually fails because of all the stormwater impoundment. So essentially the fence is not strong enough to hold up or hold back all of this sediment-laden water so you have sediment-laden discharge. So what we did is we did some modifications to the design. So we changed out the smaller T-post for a larger T-post. So these are 1.25 pound per foot T-post. We reduced spacing from 10 foot to 5 foot. We reduced the height of the fence from 32 inches to 24 inches. And then we implemented an offset trenching methodology. So this is how we actually attach the geotextile to the ground, into the soil. And we were able to improve the structural capacity of the silt fence by doing this particular type of analysis. Some other things that we've tested in the large-scale testing apparatus is manufactured silt fence systems. So this is going back to that red stripe geotextile that we analyzed in the small scale. So this red stripe manufactured system is a monofilament geotextile with a polypropylene reinforcing backing attached to hardwood stakes that are spaced 4 feet apart. We also looked at the green stripe manufactured silt fence system. So this is a very similar setup, except for the geotextile actually has woven belts, that's the green stripes that are in the geotextile, that are considered the reinforcing strips. So instead of having a polypropylene netting backing, we have built-in reinforcing into the geotextile. So this is another type of practice that we evaluated. We actually looked at several different types of manufactured sediment barriers, such as a straw log. So we looked at these different types of straw logs installed in various manners. So we did straw logs sitting on the ground surface. We did straw logs entrenched 2 inches into the ground, as well as straw logs sitting on top of a geotextile like barrier that kind of help prevent undermining during testing. We also looked at compost logs installed in a triangular fashion. So we have another tubular device, but instead of having straw, we have compost within these logs. And we actually did analysis on these as well. And then the last manufactured sediment barrier product that we looked at was the Excelsior log. So this is a square block that is filled with Excelsior fiber, and it is entrenched in the ground 2 inches and then held in place with stakes and rope. So when we actually compiled all the sediment retention data for these, we found that the non-woven silt fence installation had an improvement of roughly 10% for sediment retention just by changing the design of the installation itself. We found that the red stripe, green stripe manufactured silt fence systems had sediment retentions of 90% and 85% respectively. And then the manufactured products that we tested, that was the straw log, the compost log, and the Excelsior log, we had sediment retentions of 82%, 80%, and 84%. And these retentions were lower mainly because we saw a lot of undermining when we evaluated these practices. That's because these practices are either sitting on top of the ground or are very shallow, trenched into the ground, whereas all the silt fence systems are actually entrenched in the ground at least 6 inches. So that helps improve that sediment retention process. So just some final thoughts on what we did for this practice. So research has shown that the standard ASTM testing methodologies can be improved by incorporating regionally specific rainfall distribution and soil loss calculations. If geotextile performance properties are of interest, opt to use a small-scale testing technique. And if the sediment barrier installation performance properties, so this is how everything works together, are of interest, opt to use the large-scale testing technique. If you have any questions, feel free to reach out to me. Again, my name is Blake Whitman. I'm a assistant professor at MTSU in the School of Concrete and Construction Management. My email is blake.whitman@mtsu.edu. And I would like to just mention that this research was sponsored by the Alabama Department of Transportation, and we really appreciate their support and allowing us to be able to do this research. And with that, that ends the presentation. Thank y'all.
Hello. My name is Jay Sprague. I'm the Laboratory Director at TRI Environmental, South Carolina. This presentation will discuss the standardized test methods and test results of a large catalog of existing sediment retention device testing. This data is analyzed to determine product performance, and guidance is provided on SRD selection based on the desired balance between flow rate and sediment retention during construction operations. Sediment retention devices, or SRDs, include silt fence, wattles, filter logs, compost socks, and various types of stormwater inlet protectors, and are a widely used BMP to provide sediment filtration in stormwater runoff while allowing water passage. SRDs are frequently selected without knowing if the device will be sufficiently effective in providing the desired balance between flow rate and filtration efficiency. A sizable database of objective performance data has been developed based on recognized standard ASTM test procedures. The database includes data determined using both the bench scale standard test method ASTM D5141 and the large scale standard test method ASTM D7351. Both ASTM D5141 and ASTM D7351 are able to quantify sediment removal and associated flow rate through an SRD. However, each test method has its benefits and limitations. Test method ASTM D5141 quantifies the ability of an SRD to retain sediments carried by flowing water under bench scale conditions. 50 liters of clean water and 0.15 kilograms of test soil are mixed together and delivered through a valve to the upstream face of the SRD. The default soil mixture is described in the table. All water and sediment passing the SRD is collected and vacuum filtered to determine dry mass of sediment passing the SRD. This mass is compared to the introduced mass of soil to determine filtration efficiency. Also, SRD flow rate is calculated based on the time required for the influent volume to pass through the SRD. In this slide, we have both a plan view of the 5141 test apparatus and an image of the fabricated 5141 apparatus used by TRI. ASTM D7351 is a standard full-scale performance test commonly used to characterize installed SRD system performance, including sediment and water retention, and structural behavior under hydraulic loading. D7351 is used to quantify the water and sediment retention effectiveness percentage of the SRD under full-scale, as installed, conditions. The mixing and collection tanks are separated by areas or zones as shown here. A non-permeable slope surface immediately below the mixer spreads and directs the initial discharge to the installation zone, which is comprised of prepared subgrade to allow full-scale installation of the SRD to be tested. The area below the installation zone is non-permeable, allowing runoff passing the SRD to discharge to a downstream collection tank. The modified universal soil loss equation is used to produce test quantities of runoff of 2,250 kilograms and sediment load of 136 kilograms for a 20-foot linear SRD installation. This equates to a sediment concentration of approximately 6%. A constant discharge from the mixing tank is released evenly across the slope for 30 minutes to replicate the peak 30 minutes of the prescribed storm event. Periodic influent and effluent grab samples are the primary data collected. The depth and weight of the collected seepage inside the collection tank is measured and recorded at the same intervals. Observations such as height of ponding, undermining, overtopping, and the associated times are recorded. Grab samples are evaluated in a lab to determine percent solids content. to determine the percent sediment retention efficiency of the installed SRD. This graph presents results of D5141 testing of a wide range of SRD types commonly used in linear toe-of-slope applications. SRDs tested include woven and non-woven geotextile silt fence, proprietary composite and woven silt fence, and three-dimensional fibrous wattles. The data shows a clear delineation between product types and their relative performance in both filtration efficiency and flow rate. This data is comprised of 6 nominal categories of products tested using ASTM D5141. The findings, based on product categories identified by the authors, will be discussed in the following slides. Woven slit film geotextile silt fence. This category of filtration component provides excellent filtration efficiency across all tested products. All of the 32 tested products provided greater than 80% filtration efficiency. However, this category of product is also the category with the lowest flow rate in general. These results point to a critical issue: excessive ponding. Excessive ponding may be an acceptable risk when slit film fabric is used to protect sensitive water bodies, but may be an unnecessary risk along roadways when excessive ponding could lead to roadway flooding and risk to motorists. Woven monofilament geotextile silt fence. This product category provides moderate filtration efficiency, providing between 65% and 85% and moderately high yet relatively uniform flow rate. This product category may be exceptionally valuable to designers in areas where the risk of excessive ponding and roadway flooding would lead to unnecessary motorist risk, but where downstream impairment is of relatively low risk. Non-woven geotextile silt fence. This product category in general provides excellent filtration efficiency, with all tested products providing greater than 95% and moderately high yet uniform flow rate. Non-woven fabrics are commonly utilized for filtration because they are able to retain very fine soil particles while maintaining higher flow characteristics than a comparable woven product. Non-woven composite geotextile silt fence. Aside from the 2 noticeable outliers in the graph, this product category provides excellent filtration efficiency, with all products providing greater than 90%, and a high flow rate. Non-woven composite geotextiles are typically composed of a multi-layer non-woven geotextile component filled with natural fibers. Three-dimensional filter socks and fibrous wattles. This product category provides moderately high filtration efficiency, with all tested products providing greater than 80% filtration efficiency and excellent flow rate. Three-dimensional filter socks and fibrous wattles are generally composed of either a geosynthetic fabric or mesh filled with compost, rock, straw, or other agricultural or synthetic media. This product type typically provides a much lower vertical profile. This lower vertical profile may lead to more frequent maintenance requirements to provide consistent performance. Proprietary woven geotextile silt fence. This product category provides poor filtration efficiency but high flow rate. By design, the target use is for special conditions such as a pre-filter or as a filter to prevent trash migration without runoff impoundment. This table provides comparative results for D7351 testing that was used for the evaluation of 12 unique two-dimensional silt fence SRD products and 10 unique three-dimensional SRD products in this research. All of the products were subjected to the theoretical 30-minute peak discharge of a design storm event as prescribed in the standard. there was a clear delineation in performance between the two-dimensional and three-dimensional SRD products. Primary findings are discussed in the following slides. Two-dimensional SRD products tested via D7351 provide consistently high sediment retention efficiency, with all tested products providing no less than 82%. However, within this product category, water retention efficiency ranges greatly from 7 to 98%. Products with lower water retention efficiencies are typically composed of plastic monofilament yarns, while products with higher water retention efficiencies are typically composed of slit film. Clearly, woven geotextiles, depending on their material composition, can provide both the sediment and water retention efficiencies necessary for a variety of specific applications. All three-dimensional products provided high sediment retention efficiencies with performance ranging from 88 to 98%. However, as opposed to two-dimensional SRDs, three-dimensional SRDs have a consistently high flow rate. But caution is in order. As discussed previously, the low profile of three-dimensional SRDs can lead to a requirement of more frequent maintenance to maintain product performance. This graph combines all test results into a single graphic to better see the relationship between bench scale and large scale test results. It is quite clear when comparing data from D5141 to D7351 for similar product categories that in all cases, large-scale testing produced lower slurry water flow rates and higher filtration efficiencies. This makes sense when it is considered that D7351 testing is done with a higher sediment concentration, 6% versus the 0.3% sediment concentration in D5141, providing much more sediment to deposit on and in front of the device, enhancing removal, but reducing seepage. This paper has presented robust data via two standardized test methods on the performance of both SRD filtration components and as-installed SRD systems. There are clear performance differences using both methods when evaluating filtration components and installed systems. Data from the presentation can be used to make educated decisions on the appropriate SRD product category or system that should be used for a given sediment control application during construction.
Hello, everybody. My name is Britt Fawcett. I am the Research and Technical Services Director for Filtrex International. Welcome to Geosynthetic Advancements in Sediment Control Technologies, Socks and Waddles in Evolving Technology. One of the key things I want to talk to you about in our short time together today are the three key drivers that are influencing the development, adoption, and really the evolution of these technologies. Number one, we are seeing an unprecedented change in our land use patterns, really from the past several decades, but more so really in the past several years. And you see that depicted on the slide here as we change our land use patterns from natural systems to greater land development, land disturbance, and urbanization. What happens is we have a much higher incidence of stormwater or surface runoff. And we know there's tons of research that shows this now, that the more surface runoff we have, the more associated pollutants or pollutant load within that runoff. And every bit of all of that is getting into our receiving surface water bodies, leading to greater water quality impairment. And here's a little teaser. We don't really have to look farther than what you see on the left here in these natural systems on what some of these solutions are. So the point is, we need more high performance technologies and evolution in technology to be able to handle this greater stormwater and the greater pollutant loads that we find in our stormwater. According to the US EPA, 3/4 of all Americans live near polluted water bodies. It's not the only reason, but it is in large part because of what I described in the previous slide. The number one source of water pollution in the United States the previous year, and really every year that the US EPA records this, is sediment. It is the number one source of water pollution in the United States. And it's not just any sediment, it's really the fine sediments that lead to water quality impairment. It's those sediments that come from clays and fine silts that really stay in suspension, that lead to high suspended solids and turbidity, or really the cloudiness of the water. The second key driver is a request coming from federal and state regulators, landscape architects, and engineers to utilize and use more natural materials in our landscapes and in our watersheds to manage the increase in stormwater management and to help better filter and to target sediment and other associated pollutants in our stormwater. The idea behind this is biomimicry, or innovation inspired by nature. If we take a look at the evolution of historic and current best management practices used for sediment control and stormwater filtration, we'll see this trend already occurring from the use and adoption of silt fence and utilizing natural materials present with straw bales and mulch berms, and really evolving into the more widespread use and adoption of socks and wattles like we see today, most prevalent in the use of compost filter socks, fiber rolls, and straw wattles. The third and final driver in the adoption and evolution of these technologies is the geosynthetic advancements in the mesh containment systems for these natural organic materials. Now today this is mostly prevalent in extruded HDPE materials, and then also in knitted yarns, mostly using polypropylene. These advancements in these mesh materials have done is allowed us to create a containment system for these natural organic materials, and it's made it much easier to pre-manufacture these products and these technologies. Previously, we would have to take these organic materials in bulk to the job site and manufacture them on the actual site prior to installation and use. Now we're able to do that in a central location and then get them into the distribution network and take advantage of different distribution lanes and or take them directly to the job site. It's also allowed us to put them directly onto a pallet and transport them anywhere we want. So transportation is also much easier. It's much easier to deploy these onto a site and allow for faster installation. If we don't have the logistics of having to source and separate materials, bulk materials on the job site during construction sequencing, it makes it a lot easier to take these materials and then install them if they're already manufactured. It also makes them much easier to move around on the site. So if they need to be moved from point A to point B, they may have been installed in the wrong spot, or they need to be, a portion of them needs to be moved. If they're in a containment system, it is much easier to do that than if they're in a loose bulk form. Because they're now contained in the mesh containment system, we can now put them in a high surface flow or concentrated flow applications, such as inlet protection or check dam applications, whereas we would not be able to do this with loose organic materials. We're now seeing these mesh materials being developed specific for the application or the intended use. So we're seeing them developed for short-term projects and short-term applications, as well as more long-term applications, or where the mesh needs to be more durable, for example, on a impervious surface, on a streetscape or different hardscapes. Oftentimes the extruded HDPE is used for these short-term applications, and the knitted polypropylenes are used for these more durable and long-term applications. And that really takes us to the present day. What's happening in the last couple years today, and really where I see the biggest advancements and really the evolution in these technologies, is that new mesh materials are being made with natural fibers and bioplastics and biopolymers to create a fully 100% biodegradable technology or product. And what this allows us to do is we have a zero waste product. We can leave the entire technology or the entire BMP or product on the site, and this eliminates expensive removal, which is a high labor cost, and disposal cost by taking it to the landfill. By combining these natural organic materials with geosynthetic mesh containment systems, we're now able to put these technologies in a much more varied uses and applications. And what you see here are a variety of generic applications and practices where we can use socks and wattles. And you'll see that the vast majority of them are used in erosion and sediment control or construction activity applications, but they are also used widely in post-construction stormwater management applications as well. Because these technologies have evolved quite rapidly and at the request of many of these federal and state agencies, and because we're able to put them in so many different practices or applications on a job site or in a watershed, we're now seeing most of these federal agencies and state agencies that have the ability to create a standard specification, approved products list, or some sort of guidance document for these practices are now doing that and publishing these in their state or federal manuals. Now, there are some differences between some of these socks and wattles. Not only do they use different source materials, natural materials, organic materials on the inside, but one of the key differences are the particle sizes of that fill material or of that filter material. And you'll see in this graphic, as those filler materials are more coarse in nature, and you see in particle sizes in inches across the bottom, as those particle sizes get larger or more coarser, they create more pore spaces within the product or within the technology, and that allows for a greater water flow through rate. And then you also see it acting more like a filtration device. And as those particle sizes get smaller and smaller, you reduce pore spaces basically down to zero, and what you have is a solid barrier or a dam or something that just restricts flow. And so it can work quite well in low flow type environments or where just flow restriction is all you need, but they will quickly go into bypass through overflow or end-around flow type situations. So you see some that are specifically designed for this, and you see others that are specifically designed for high flow and then also filtration mechanisms. And then you're also seeing really this development and research in this space to develop sort of the holy grail of these technologies, and that is to have both high flow and high filtration within the same technology or product. And it's really this optimum performance zone that I've highlighted here in the slide. Now, there's been quite a bit of scientific research that's been published in the scientific literature over the past few years. This is a research project commissioned by the USDA Ag Research Service outside of Washington, D.C. It's been published in the Journal of Soil and Water Conservation, where they evaluated silt fence and filter sock, and you can see the percent reduction in total suspended solids and turbidity for both of these technologies. A similar project conducted by the University of Georgia, also published in the Journal of Soil and Water Conservation, evaluated the total suspended solids reduction of compost filter sock compared to a uncontained mulch filter berm and straw bale, and you can see the significant difference in performance between these two types of practices, really about 60% effectiveness or percent removal of sediment versus about 85% effectiveness or percent suspended solids removal efficiency for the compost filter sock. And finally, a study conducted by San Diego State University utilizing a modified ASTM standard under large-scale test conditions, comparing a filter sock to a silt fence and a straw wattle. And you can see the total sediment or total solids removal efficiencies on the right-hand side of the table. And then finally, one of the other key differences in the type of media or material that you can put inside the containment system will allow you to target different types of pollutants that we find in post-construction stormwater. Now, some of these natural materials or organic materials are relatively inert, and they're designed really to target sediment through physical filtration or physical sediment deposition means. But there are other organic materials and natural materials that actually have the ability to sorb or adsorb some of these soluble form pollutants that we find that are very prevalent in post-construction stormwater, whether it's on industrial sites or MS4 sites or anywhere in urban stormwater runoff. Examples include nitrogen species, phosphorus species, total coliform, E. coli, heavy metals. In this particular study, they evaluated copper, cadmium, chromium, nickel, lead, and zinc, and then also petroleum hydrocarbons. So really some of these materials can act as true biofilters, not just in the sediment control context, but also in the post-construction stormwater filtration context as well. And we've reached the end of our time together. Thank you for your time. If you would like to reach out to me or have a question about anything you've heard in this presentation, please jot down my information and reach out to me either by phone or through email. And I look forward to hearing from you. Thank you very much.
Welcome to Use of Geotextile Filtration Fabrics with Skimmers for Stormwater Quality. My name is Jamie McCutcheon. I am a 1992 graduate of Clemson University with a BS in Civil Engineering. I have been working in the stormwater industry either as an engineer since 1994 or as a manufacturer since 2013. I'm a licensed professional engineer at North Carolina, South Carolina, and Georgia, and a member of ICA and CESWA. This presentation is on a technical paper for use of geotextile filtration fabric with skimmers for stormwater quality. So a little background information. Skimmers have been around for many years and promoted for use in sediment basins during construction to meet surface withdrawal requirements. Stormwater basins retain water and typically rely on settling to meet water quality requirements for post-construction. The use of skimmers as part of the permanent outlet will increase trapping efficiency due to the surface withdrawal. Ponds without a skimmer typically withdraw from the bottom where sediment accumulations are the highest. As you can see from these photos, a typical perforated riser has an outlet orifice at the very bottom of the riser and obviously takes in a lot of mud as it discharges stormwater. Ponds with skimmers withdraw from the surface or near the surface, allowing sediment to settle to the bottom and releasing the cleaner water from higher in the water column. Skimmers are well documented to help with trapping efficiency during construction. So can they also help post-construction? It would make sense that surface withdrawal as part of the post-construction outlet would aid in meeting water quality requirements. Skimmers also can reduce maintenance and make it easier to clear clogs in post-construction systems. So current stormwater standards began with the 1972 Federal Clean Water Act and National Pollutant Discharge Elimination System Program, or NPDES program. The Phase 1 Municipal Separate Stormwater System Program, or MS4 program, was established in 1990 for municipalities with population of more than 100,000, and the Phase 2 MS4 program began in 2003 for populations of 10,000 to 100,000 to require coverage under NPDES program. So under the NPDES program, the EPA issues construction general permits to most states. These are typically 5-year permits that must be renewed, and each time they're renewed, it is typical for additional requirements to be added. When the program began, it focused primarily on quantity management for like the 2-year, 10-year, 25 or 100-year storms. More recent permits have added water quality requirements. And the majority of states now require surface withdrawal for sediment basins during construction, which is primarily accomplished through the use of skimmers. So why use skimmers with geotextile filters in permanent basins? As we mentioned, surface withdrawal will increase trapping efficiency. The additional filtration can be added around the skimmer to further reduce pollutant discharge. Research has been underway to determine an effective way to filter for TSS, as well as ways to incorporate media to target pollutants of concern, such as phosphorus, hydrocarbons, metals, or others. Currently, extended detention for water quality is a common way to design post-construction basins to meet water quality requirements. However, there are several flaws with the designs. The basins are designed to capture pollutants by holding runoff for an extended time and allowing for settlement. This is typically based on a 1-inch runoff over the contributing drainage area to that basin. The basins that rely on settling time provide very little treatment for smaller storm events due to limited ponding or holding time for smaller storms. In addition, the volume-based design results in larger pond sizes or larger underground storage volumes, which don't necessarily provide an increased benefit. What are the benefits to filtration versus settlement in basins? Ponds provide a large containment volume to reduce maintenance frequency and treat larger drainage areas. There is excellent potential to retrofit older basins that did not include water quality benefits using a filtration system. You would not be able to necessarily do that using a settlement system, as the basins do not have the necessary volume to meet these requirements. Using filters in ponds are relatively easy to access and maintain, especially when you compare that to other systems that use underground vaults and may require confined space entry for maintenance. Other benefits to filtration versus settlement include that the peak rate of discharge can be increased based on filter capacity, which can result in significantly smaller pond volumes. Using a filter-based approach, the filter treats 100% of runoff from storms at or below the water quality design event, even on the much smaller storm events that do not get well treated based on a settling design. Also, as we mentioned, the filtration media can be customized to target specific pollutants of concern in areas that have a TMDL in place or specific impairments in water bodies. So there are benefits to using skimmers paired with filtration in basins. The skimmer can be sized to control the peak rate for lower storm events, such as the 2-year storm or whatever the lowest storm event required in that MS4 is. The skimmer increases filter efficiency by withdrawing from the surface where the water is cleaner. Therefore, the filter tends to last longer. The skimmer also makes it easy to access or pull to the side of the basin the skimmer for maintenance and changing of filters. There are challenges to using skimmers with filtration. Filters are prone to clog over time and will require maintenance and periodic cleaning or changing of the filters. The skimmer must be durable and last for more than a few years to be suitable for permanent use. Many skimmers are made of PVC and would not be suitable for post-construction outlets. Also, there are no established standards currently for basis of design and permitting based on a combination of use of a basin and filtration. There are some established testing protocols. There are currently 2 widely recognized testing protocol programs: the Washington Tape program from Washington State and the NJCAT certification program out of New Jersey. NJCAT has established testing procedures for filtration manufactured treatment devices, or MTDs. These standards must meet minimum removal percentage of TSS and a minimum of a 1-year service life or greater of the filter to be certified by NJCAT. We have gone through several rounds of testing with the intent of coming up with a system to meet NJCAP protocols. Our first round of testing used a woven geotextile that had an apparent opening size of 45 microns and a flow rate of 22 gallons per minute per square foot. The results from our round one determined very quickly that this flow rate was insufficient to keep up with and maintain the skimmer flow. Our second round of testing also tested a woven geotextile, had an AOS of 40, and a much higher flow rate of approximately 145 gallons per minute per square foot. This testing, the improved flow, but began to blind after several trial runs. It did significantly help in keeping trash and debris away from the outlet of the skimmer. It did not have much impact on turbidity, as you can see from this photo, as the water inside the filter and outside are essentially the same. During this testing, there was also a skimmer without an outlet. As you can see from this photo, trash and debris were able to get to the outlet much quicker and cause it to start clogging. For our third round of testing, we went with a non-woven geotextile in hopes that it would not blind off as quickly. This was a medium flow non-woven with an AOS of 50 and a flow rate of 55 gallons per minute per square foot. We had a surprising result in that vegetation began to grow in the fabric when it was left in the pond. We determined that this fabric with the low flow rate was not suitable. We also tested this by opening the fabric at the bottom to allow greater flow, but this was also insufficient. And the blinding and vegetation growth were obviously a significant issue with use of this material. For the fourth round, we tested a high-flow, non-woven geotextile in a two-layer system to give a larger surface area. We built a basket to hold the material away from the skimmer. It had an AOS of approximately 100 and a flow rate of 140 to 150 gallons per minute per square foot. So our results with this system were better. The fabrics with a higher flow rate were showing significant potential. They provided very good filtration, but it needs sufficient surface area to meet the flow of the skimmer. We also noticed that the flow rates achieved in the test facility were significantly less than per ASTM D4491 testing of the fabrics. The use of the skimmer to pull flow through the fabric resulted in a much lower flow rate. The fabric did not keep up with the skimmer flow as well as desired, and in this case the basket was too buoyant and actually tended to float up with the skimmer, and so additional weight needed to be added. Round 5 of testing included a basket that was made of metal instead of HDPE. We tested the high-flow non-woven geotextile. This time we put the geotextile in strips and overlapped them. And then we also had 2 offset inner layers of a courier filter material and had an opening at the bottom of one layer and top of the other layer so that water could pass through the filters or through the system without going through the filter in case it was completely clogged. The materials had an AOS of 100 or more and a flow rate of 100 to 150 gallons per minute per square foot or more in the case of the courier material. So our results were better this time in that the flow rates of the geotextiles generally kept up with the skimmer flow rate. It provided very good filtration even with the open bottom of the basket. We also used dye in the water to check for flow at 2 places, both the opening of where the pipe comes out of the basket and at the bottom of the skimmer since there was not a bottom filter. In both cases, we did not notice a substantial pull of the skimmer, based on the dye in these areas. We also were using a weir tank for the flow rate testing, and the water in the weir tank was relatively clear, indicating excellent performance of sediment and pollutant removal. We removed the outer non-woven geotextile layer to examine the courier material on the inside. The courier fabric trapped debris but did not show any blinding. The courier material also provided very good filtration of whatever passed through the non-woven material. So we realize our next steps are to develop a multi-stage filter system with sufficient surface area to maintain the skimmer flow rates and minimize blinding. Once this is established, we will begin third-party testing per the NJCAP protocols to confirm TSS removal efficiency. And once that's successful, we will develop a commercially viable system that can be deployed in wet or dry basins to meet a wide variety of local water quality requirements, as currently there is no established national standard. So in conclusion, combining geotextile filters with skimmers does show significant potential to aid in meeting stormwater quality requirements in detention basins. The differences in flow based upon ASTM D 4491 and in situ testing is significant and must be verified by third-party testing. Additional research is necessary to develop a commercially viable product. Lastly, the addition of media to target pollutants other than TSS will require additional research, including scale testing to confirm viability. Some of these will be relatively simple, such as adding an oil boom around the skimmer to target hydrocarbons. However, others, such as trying to remove phosphorus from metals, will take much more research. Thank you for watching use of geotextile filtration fabrics with skimmers for stormwater quality. Again, my name is Jamie McCutcheon with Rymore Waterworks, and my contact information is here if you have any questions.